Welcome to the Deep Dive. We're here to break down complex, world-shaping topics into the core ideas you really need to grasp.
And today, we're tackling a big one, quantum computing.
Definitely big. It's this technology that, promises to solve problems we currently think are impossible. It feels like it's really shifting from pure physics theory towards, well, actual engineering challenges now.
Exactly. And the potential impact is just immense. We're talking about things that could totally reshape cybersecurity, massively speed up drug discovery, optimize huge logistical networks.
Things that currently involve a lot of guesswork or just brute force computation.
Right. And that's not even mentioning advanced AI or, climate change modeling. The stakes are really high.
So our mission today is to get past the buzzwords. We want to unpack the fundamental ideas that give quantum computers this almost unbelievable power.
We need to talk about bits versus qubits and then those really core quantum concepts, superposition and entanglement.
Okay, let's start there. Why do we even need something beyond classical computers? Where do they hit their limits?
Well, classical machines use bits. Simple switches, right? Either 0, 1, a definite state. And crucially, they process information sequentially, one calculation after another.
Okay, step by step. But that creates a problem when things get really complex, doesn't it? This idea of combinatorial complexity.
Precisely. If you have a problem with tons of interacting variables where the number of possible combinations just explodes exponentially, think about optimizing a delivery network for thousands of trucks, or figuring out the precise structure of a complex drug molecule.
So checking every possibility one by one just takes too long.
It can take literally centuries, even on the fastest supercomputers today. They just aren't built for that kind of exponential scaling problem. They hit a wall.
A very hard wall. So how does the quantum approach get around that?
It starts with a fundamentally different building block, the quantum bit, or qubit.
Okay.
Now, if you have, say, n classical bits, you can represent only one specific state out of the 2 to the n possibilities at any given moment.
So 10 classical bits can store just one pattern out of a 1024.
Exactly. But here's the quantum leap, the punchline.
Mm-hmm.
A quantum computer with n qubits can exist in a state that represents all 2 to the n possibilities simultaneously.
All of them at once. So the 10 qubit system is somehow holding all 1024 states.
In a manner of speaking, yes. It's exploring that entire space concurrently. And the power just scales incredibly fast. Jump to 50 qubits, and you're looking at over a quadrillion states being processed in parallel.
Wow. Okay, that's the exponential advantage right there, this quantum parallelism.
That's the core idea. It's not about replacing your laptop for email, It's about opening up computation for specific types of problems that are just impossible classically.
And this power comes from tapping into the, well, frankly, the weirdness of quantum mechanics. Let's get into the first principle. Superposition.
Right. Superposition is fundamental. A classical bit has to be either 0 or 1, no ambiguity.
No.
A qubit, though, can be in a combination of both 0 and 1 at the same time. It exists in a sort of probabilistic blend of states.
The usual analogy is the spinning coin, right? Classically, the coin has landed heads or tails, 0 or 1.
Exactly. But the qubit in superposition is like that coin while it's still spinning in the air. It's potentially heads and potentially tails simultaneously.
Until you stop it, until you measure it.
Precisely. And this ability to hold multiple values at once is what enables that quantum parallelism we talked about. It lets the computer explore many paths simultaneously.
Okay, so that's superposition, holding multiple possibilities. What about the next concept, entanglement? That one seems even stranger.
Yeah, entanglement is, well, Einstein famously called it spooky action at a distance. It's a unique quantum connection where 2 or more qubits become linked, inseparably correlated.
Linked how? Even if they're far apart?
Doesn't matter how far apart. Miles, light years, theoretically, their fates are intertwined. If you measure the state of one entangled qubit, say, you find it's a 0, 1, you instantly know the state of its entangled partner must be the opposite, a 1, or whatever the specific correlation dictates.
Instantly. Faster than light.
The knowledge is instant. It's a correlation, not communication in the classical sense. But yeah, that instantaneous link is real and deeply weird. It's like having, I don't know, a pair of magic coins. If one lands heads, the other instantly becomes tails, wherever it is.
That non-local connection. It's hard to wrap your head around. How is that useful?
It's crucial for complex quantum algorithms. It allows the states of multiple qubits to be coordinated in intricate ways, letting them work together almost like a single computational entity, amplifying correct answers and canceling out wrong ones through interference.
But this power comes with a huge catch, right? This idea of measurement collapse.
Yes. The observer effect, essentially. This is the critical, almost frustrating part of quantum computing.
Okay.
While the qubit is in superposition, it holds all that rich quantum information, but the moment you try to look at it, the moment you measure it to get an answer,
A pick us aside.
exactly, it collapses. It's forced into a single definite classical state, either 0 or 1, and all that quantum parallelism, that richness of being in multiple states, it vanishes.
So the very act of getting the answer destroys the quantum advantage that produced it.
In that qubit, yes. Which means quantum algorithms have to be incredibly clever. They need to manipulate these quantum states, let them evolve and interfere, all while avoiding measurement until the very last step.
Delaying the collapse until the calculation is basically done.
Right. You want the final measurement to reveal the answer that's been amplified through the quantum process. It's a delicate balancing act.
Okay, so if we can manage that balancing act, keep things quantum long enough, what's the big payoff? What's the application that has everyone, especially in security, so concerned?
That would be Shor's algorithm. Peter Shor figured out, back in the 90s, a quantum algorithm that can find the prime factors of very large numbers.
Factoring large numbers. Why is that such a big deal?
Because almost all of our current public key encryption, the stuff that protects emails, banking, secure websites, everything relies on the fact that factoring huge numbers is incredibly hard for classical computers.
Like RSA encryption, Diffie-Hellman, that kind of thing.
Exactly. Their security is based on that classical difficulty. Shor's algorithm proves a large enough, stable enough quantum computer could break that difficulty exponentially faster. It basically finds the keys to the kingdom.
Okay, that's a serious threat to global security infrastructure.
Yeah.
So what's the defense plan?
It's sort of a two-pronged approach. First, there's post-quantum cryptography, or PQC.
PQC, so new algorithms.
Yep. Entirely new types of cryptographic algorithms, things based on lattices or hashes, different mathematical problems. The key idea is that these new problems are believed to be hard for both classical and, crucially, quantum computers to solve.
So PQC algorithms could run on our current computers, our existing internet infrastructure, but be resistant to future quantum attacks.
That's the goal. NIST, the U.S. standards body, is in the final stages of standardizing these PQC algorithms now. It's about changing the mathematical locks, essentially.
Okay, changing the math. What's
Yeah.
the second up? You mentioned two prongs.
The second is quantum key distribution, or QKD. This uses quantum physics itself to secure the communication channel.
How does that work? Does he use entanglement?
It often does, yes. Protocols like BB84 leverage quantum properties. Imagine two people, Alice and Bob, sharing a secret key using entangled photons. If an eavesdropper, Eve, tries to intercept and measure those photons to steal the key.
The measurement principle. Looking at it collapses the state.
Exactly. The very act of eavesdropping inevitably disturbs the quantum states of the photons. Alice and Bob can then run checks and detect that disturbance. They'll know someone is listening.
So the physics itself guarantees that any attempt to spy is detectable, making the key exchange theoretically unbreakable.
Theoretically, yes. That's the promise. The big difference is PQC is software for today's hardware. QKD requires building entirely new quantum communication hardware, special fiber optics, quantum repeaters, things like that. It changes the physics of the communication, not just the math.
Got it. So beyond breaking codes and securing communication, where else does this quantum advantage really shine? Science seems like a huge area.
Absolutely. Molecular simulation is a prime example. Classical computers really struggle here.
Why? Because molecules themselves behave quantumly.
Precisely. The interactions between atoms, the way electrons behave, it involves superposition, entanglement. It's fundamentally quantum. Trying to simulate that accurately with classical bits is incredibly inefficient. Again, that combinatorial explosion.
So you need a quantum computer to efficiently simulate a quantum system, like a molecule.
Exactly. Quantum computers are naturally suited for this. They can model these interactions much more accurately, potentially revolutionizing things like drug discovery, materials science, designing new catalysts, or batteries.
Oh, there's specific algorithms for that?
Yeah, one key type is the variational quantum eigensolver, or VQE.
VQE. Okay, that sounds complex. What's the elevator pitch? What does it do?
Yeah, it's a bit of a mouthful. VQE is actually a great example of a hybrid algorithm. It
Yeah.
uses the quantum computer for the really hard part, calculating the molecule's lowest energy state, its ground state energy. That's a tough quantum calculation.
Okay, the quantum computer does the heavy lifting there.
Right. But then it uses a classical computer to tweak the parameters, to optimize the process, and guide the quantum calculation towards the right answer. It's a way to get useful work out of the somewhat noisy quantum processors we have today.
Hybrid approach. Makes sense. And that simulation capability extends beyond molecules.
Right.
You mentioned climate science.
Yes, modeling climate systems involves an enormous number of interacting variables. Ocean currents, atmospheric chemistry, feedback loops. It's another area where classical computation struggles with the sheer scale.
The quantum computers could potentially give us much more accurate, faster climate models, helping predict extreme weather, maybe test mitigation strategies.
That's the hope. It could be a powerful tool for understanding these incredibly complex systems.
And what about AI? Seems like everything connects to AI eventually.
Well, training large AI models, especially deep learning models, is incredibly computationally intensive. It can take weeks or months on massive clusters of GPUs.
Right, it's a huge bottleneck.
Quantum computing might offer ways to dramatically speed up parts of that process, particularly optimization tasks common in machine learning. Faster training could lead to more powerful AI for things like medical diagnosis, financial modeling, pattern recognition, you name it.
So the potential is clearly enormous across the board. But let's ground ourselves in reality. Where are we now? You mentioned noisy processors.
We are firmly in what's called the NISQ era. NISQ, Noisy Intermediate Scale Quantum.
Noisy being the key word there.
Absolutely. Today's qubits are, well, they're finicky. They're incredibly sensitive to their environment. Any little bit of heat, stray electromagnetic fields, even tiny vibrations can cause them to lose their delicate quantum state. That's called decoherence.
Decoherence. So the quantumness just fades away.
Pretty quickly, yeah. Maintaining that quantum state, keeping the qubit coherent is maybe the central engineering challenge right now.
It sounds like trying to keep a soap bubble from popping in a hurricane. If superposition is the power, decoherence is its kryptonite.
That's a pretty good analogy. It requires extreme isolation, often cooling things down to temperatures near absolute zero, meticulous shielding. It's incredibly difficult engineering.
How do researchers deal with this noise and fragility then? You can't run Shor's algorithm on a machine that keeps making errors, right?
Not reliably, no. The long-term solution everyone is working towards is quantum error correction, or QEC.
Okay, error correction, like we have in classical computers.
Sort of, but much, much harder in the quantum world. Techniques like surface codes aim to build fault-tolerant quantum computers, but they require massive overhead, meaning you need to use many physical, noisy qubits just to encode and protect a single, stable, logical qubit that you can actually compute with reliably. Hundreds, maybe thousands of physical qubits for one logical one.
Wow, so we need way more qubits than we currently have just to make them reliable through QEC.
Exactly. And since we're not there yet, in the NISQ era, we rely heavily on error mitigation techniques.
Mitigation, not correction. So working around the noise rather than eliminating it.
Precisely. A common technique is zero-noise extrapolation, or ZNE.
ZNE, how does that work?
It's quite clever, actually. You run your quantum algorithm multiple times on the noisy hardware, but each time you deliberately increase the noise level slightly in a controlled way.
Okay, why make it noisier?
Because then you look at the results you get at these different no-noise levels. You see how the answer degrades as the noise goes up, and then you can mathematically extrapolate backwards.
To estimate what the answer would have been if there were zero noise.
Exactly. It's like plotting a trend line from your noisy data points back to the ideal noise-free axis. It's a workaround, a way to squeeze useful information out of today's imperfect machines.
That makes sense. A practical approach for the near term. This all depends on the physical qubits themselves, though. Is there one winning technology, or is it still a race?
Oh, it's definitely still a race. There's a lot of competition and several different promising approaches to actually building qubits.
What are the main contenders?
Well, one major approach is superconducting qubits. Companies like IBM, Google, Rigetti use these. They're essentially tiny electrical circuits cooled down to near absolute zero, so they become superconducting.
What are their pros and cons?
They tend to be very fast. Their gate operations manipulating the qubits happen quickly. That's a big plus. The downside is they need those extreme cryogenic temperatures, which is complex, and expensive, and their coherence times, how long they stay quantum, can be relatively short compared to some others.
Okay, superconducting. What else?
Then you have trapped ion qubits. Companies like IonQ and Quantinuum are leaders here. They use electromagnetic fields to suspend individual charged atoms, ions, in a vacuum.
Trapping single atoms.
Yep. And then they use precisely targeted lasers to manipulate the quantum states of those ions. Because atoms are identical and pristine by nature, these qubits tend to have very high fidelity. They're very accurate and much longer coherence times. They hold that quantum state for longer.
Better stability? Maybe slower operations?
Generally, yeah. The gate speeds tend to be a bit slower than superconducting qubits, so there's a trade-off.
Interesting. Any other major players in the hardware race?
The third big one to mention is more theoretical, maybe? It's the pursuit of topological qubits, which Microsoft has been investing heavily in.
Topological. What's the idea there?
The idea is to encode the quantum information non-locally. Using exotic quasi-particles called Majorana fermions, the information isn't stored in one specific point, but spread out across the structure of the qubit.
How does that help?
The theory is that this makes the qubit inherently much more resistant to local noise and errors. If the information isn't in one place, a small local disturbance can't easily destroy it. The hope is for built-in fault tolerance, potentially drastically reducing the need for that massive overhead of error correction we talked about.
So potentially a shortcut to reliable quantum computing, but maybe harder to build in the first place.
That's the gamble. It's scientifically very challenging, but the payoff could be huge if they can make it work reliably.
Okay, so we've covered a lot of ground. The basics of qubits, superposition, entanglement, the security threats like Shors, the defenses like PQC and QKD, applications in science and AI, and the current reality of NISQ, noise, and the hardware race.
Yeah, it's a fast-moving field.
If you had to boil it down, the core takeaway is that quantum computing gets its power by harnessing these fundamentally quantum effects, superposition, and entanglement.
Right. Which lets them tackle problems like factoring or complex simulations that are just out of reach for classical machines.
And for now, in this noisy era, we're relying a lot on those hybrid approaches like VQE, using classical computers to help steer the quantum ones.
Exactly. Leveraging the strengths of both is key right now, and working hard on error mitigation and pushing towards true error correction.
It really is a technology built on principles that defy our everyday intuition. We talked about QKD earlier, building secure communication, based on the fact that observing something changes it.
Yeah, using the measurement principle as a security feature. It's a fantastic practical application of fundamental quantum mechanics.
It really makes you think, doesn't it? What does it signify about, well, reality itself, that we're now engineering devices, creating technologies like unspiable communication channels based entirely on these strange, probabilistic, non-local rules of the universe? Rules where uncertainty and observation aren't just limitations, but actual tools.
It definitely signals a shift. The deepest, most counterintuitive aspects of physics aren't just for textbooks anymore. They're becoming the building blocks for our future technologies. Something to ponder, for sure.
We'll leave you with that thought. Hopefully you feel significantly more informed about this quantum revelation. Thanks for joining us for this deep dive.